So in this screencast, we'll look at alcohols and ethers. To start off Organic Chemistry 2. So what is an alcohol? Generally speaking, we can represent it as this ROH. And so the OH is the hydroxyl group. So that's what makes an alcohol an alcohol. So let's look at a couple examples of those. Starting with the C1 alcohol, CH3OH. So this R here, what we're going to look at is specific versions of that. So the C1 alcohol is methanol, CH3, that's what we mean by R, and there's our OH. So let's review our nomenclature. So it's a C1, that would be a methane derivative. So instead of methane ending with an E, the alcohol would end in OL. So that's what makes an alcohol. In the name there is the changing the E from the alkane to OL. So if we have two carbons, CH3, CH2OH, two carbons is ethane, so we drop the E at the end and add OL, so this is ethanol. So what about, let's go up to a 3-carbon chain, and so we'll use this representation now. So if we have the hydroxyl group at the 1 position, this would be 1 propanol. But also if we look, that 3-carbon unit of propane, the OH could also be at the 2 position, so this would be 2 propanol. So what we're doing now is using the locant number followed by a hyphen to specify where the hydroxyl group is. So this number is attached to the suffix, which is the main functional group, telling us where that hydroxyl group is. So let's look at one more type of alcohol here. So if we have this sort of parent here, 2-methyl propane, and the hydroxyl group is at this position, we would name this 2-methyl-2-propanol. And so now we're going to compare basically these 3 different alcohols according to how the alcohol is classified. So in the first one, this is called a primary alcohol, this is a secondary alcohol, and then this is a tertiary alcohol. So that's the classification. And really, we can think of it 2 ways. If we're looking at the carbon that is bearing the hydroxyl group, that's called a carbinol carbon. Carbinol carbon. So the carbinol carbon, if it has 1 carbon attached to it, that's primary. Carbinol carbon has 1, 2, that's secondary. Carbinol carbon 1, 2, 3, that's tertiary. So this classification scheme is very important for us in this chapter because it's going to help us understand the reactivity of the hydroxyl group under various reaction conditions, some of which we've seen already in 255, such as substitution reactions, elimination reactions, and what we'll learn this semester, oxidation reactions. So let's look at some other cases of alcohols, just so we get our nomenclature. We're on the same page with communicating. So if we have this alcohol, which is a primary alcohol, there's another term that we can also use based on this carbonyl carbon being sp3 hybridized next to an alkene. That's called an allylic position. So that's important for us. This is in terms of communicating a location of the functional group, that's an allylic alcohol. Another example, if that sp3 hybridized carbon bearing the hydroxyl group is also bearing a benzene ring. This again is a primary alcohol, but this position is now called benzylic. And we have one more example of this. The carbonyl carbon is bearing an sp hybridized carbon of an alkyne. Again, primary is the classification. This type of carbon is called propargylic. And the reason that I bring these up is because that carbon is special due to the weakness of the associated CH bonds. And that's important when we want to distinguish between different types of CH bonds in a molecule to functionalize them. One last alcohol that we need to be familiar with is the one directly attached to a benzene ring. So this would be hydroxybenzene, but it's more commonly referred to as phenol. So remember, a benzene ring is 6 carbons. It's a ring. It has 1, 2, 3 pi bonds, but as we'll see later on in this semester, we don't really consider those as discrete pi bonds due to a concept called aromaticity and conjugation. So phenol is the aromatic alcohol. So let's go ahead, and now that we have an understanding of alcohols and nomenclature, let's do a brief review of ethers. So an ether you can think of as a derivative of an alcohol in which the OH group, the H has now been substituted for another carbon-based group. So if I call these R1 and R2, you can have R1 is the same as R2, and that would be called a symmetric ether. And the name of those are pretty easy. We'll look at some of those. If R1 is not the same as R2, so it's asymmetric ether, and so the nomenclature of those gets a little bit more challenging, but it's you visually recognize that it's dissymmetric. So what are some versions of ethers? So for example, if we have CH3, O, CH3, this would be called dimethyl ether. So dimethyl, 1, 2, there's 2 of them, dimethyl, a space, and then the word ether. So what about an example that's not symmetric? Say we have methyl and then we have ethyl. So this is straightforward. We would just alphabetize it. E comes before M. So this would be ethyl space methyl space ether. So it gets a little bit more challenging in naming these when you have like branching that's occurring off these different R groups. So these are examples of acyclic ethers. A functional group that's part of this initial module, we'll look at cyclic ethers. So if you think of the smallest ring system you can have as a three-membered ring system, so if the oxygen's part of that, you have two carbons, and if they're in a ring system, this is also an ether. It's a cyclic ether. It has 1 degree of unsaturation. This is called ethylene oxide. And this is an example of an epoxide. So an epoxide is a three-membered ring. So what I'm going to do, just with color here, I'm just going to write a 3 in there. So when it's a three-membered ring, it's called an epoxide. What if we go up a ring size? So this is called oxetane. So I'm just going to write a 4 in there. So you can associate that number with the common functional group. Then a 5-membered ring. So this is called tetrahydrofuran. So these we do need to have an appreciation for these, because we're going to look at the chemistry of epoxides. We have a three-membered ring. It's strained. That means we can open it with nucleophiles either under acidic or basic conditions. The oxetane is also strained, but less so than the epoxide. And then the tetrahydrofuran as an organic molecule by itself is typically used as a solvent. But we're going to see later on with derivatives of this structure are important biologically in sugar molecules that are present in DNA and RNA. So let's briefly look at an important aspect of alcohols more so than ethers. Alcohols can hydrogen bond. So that's an important aspect to the physical properties of the bulk matter in terms of melting point, boiling point. So for example, let's look at, say we were looking at ethanol, and I've put in the lone pairs. So a molecule of ethanol can hydrogen bond with itself in the following manner. And a hydrogen bond is an attraction. And so basically for an attraction to occur, you have to have something donating and something accepting. So if I were to depict this lone pair of electrons is attracted to that hydrogen. This lone pair is attracted to that hydrogen. So it's an association of those two molecules. Now, if you think of that in terms of the bulk matter, if the molecules are attracted to one another, you're going to have to put more heat into that liquid to get it to boil. So this is an aspect in alcohols that is not present in ethers. So alcohols typically boil a lot higher than ethers do. The other aspect of this that's important is miscibility, in terms of if we're using water as a sort of standard solvent. So we would say, for example, CH3, CH2OH, and if we were dissolving that or mixing it with water, we would see that ethanol would be completely miscible with water due to extensive hydrogen bonding. So if we were to compare that with, say, diethyl ether, mixed with water, you would see that the water can act as a donor of a hydrogen bond. So it's donating OH, it's donating a hydrogen bond. The ether can accept it through that lone pair. So there still is an interaction, but notice it's only one, right? So whereas with the ethanol acts as a donor and an acceptor with the water, whereas the ether can only act as an acceptor of that hydrogen bond. So this is an example of why ethers would be less miscible in water than alcohols. So one last thing about this term bond. So a typical OH covalent bond, so the OH bond is worth 498 kilojoules per mole. So again, that's the bond association energy. When we say hydrogen bond, it's a weak bond. So by weak, it's 21 or so kilojoules per mole. So that's significantly less than your standard covalent bond. But again, all bonds are attractions between two different objects, in chemistry, in this case, the two different elements. So really, bond strength runs from a spectrum from weak to strong. And again, those things play a role in the physical properties of the compounds. So in this next slide, we're going to look at some reactions that we saw in 255 of synthesizing alcohols from alkenes. So we'll look at two examples, but before we do that, I just want to write out some rules of the arrow pushing formalism for mechanisms. So a mechanism is basically an understanding of how electrons flow in taking the starting materials to the products. So if you really want to do well and be successful in this class, it's not about memorizing reactants, reagents going to products. It's an understanding of how that happens. And through that understanding, you will then be able to predict any reaction, even if you've never seen the reagents before. So what are some rules you should abide by? So the first rule, all reactions have a nucleophile. A nucleophile is conceptually similar in reactivity to a base because they are supplying the electrons. And an electrophile. An electrophile is an acid. So again, we're thinking in the most broad sense of the acid-base reaction in terms of the Lewis definition. A Lewis base is a nucleophile, a Lewis acid is an electrophile. So all reactions will have that pair. The second thing, arrows originate from the nucleophile. And end at the electrophile. So this should conceptually make sense because the nucleophile is supplying the electrons that form the new bond, and the electrophile is accepting them. Again, when you're writing your arrows, whenever you form a bond, you must break a bond. Why? Because you still have to obey the rules for the Lewis dot structure convention. Again, you're looking at the normal valencies for each element type. And then 4, you must account for charges. And so when you're accounting for formal charges, you have to diagnose the reaction medium. Acidic reaction medium will have positive charges, whereas basic reaction media will have negative charges. So we will see that as we examine the mechanisms of how things happen and what we mean by that, and how charges move around and must be conserved. So let's go ahead and look at 2 reactions where we put this into place. So these are alcohol synthesis reactions. So we're going to start with one example here. Alkene hydration. Let's go ahead and look at this molecule, which we will call 1-butene. So this molecule has a melting point of -185 degrees C, and its boiling point is -7 degrees C. So it's a nonpolar molecule. You can see that there's not very many intramolecular or intermolecular ways it can attract itself, so the boiling point's pretty low. If we treat this molecule with water and a catalytic amount of acid, and so the square brackets around the sulfuric acid mean it's catalytic, what we're going to find is that we then make the following product. So the name of this is 2-butanol. So this has a melting point of -115 degrees C, a boiling point of 98 degrees C. And so just from this overall transformation, what should you be cognizant of? Again, we're taking a nonpolar molecule with these physical properties. We are adding the elements of water across the pi bond, and then through the installation of this hydroxyl group, we've now transformed the alkene into an alcohol. This is a secondary alcohol. Notice the physical properties change, specifically the boiling point. This is much higher, and again, that's due to the hydrogen bond capability of that functional group. So these are the associations you want to make throughout this semester, and why these reactions are important. Because we're changing the physical properties, we can now do things with this molecule that are not possible with that molecule. So how exactly does this happen? What is happening mechanistically? How can we rationalize it with the arrow pushing formalism and these rules shown up here? So if we're looking and just keeping sort of count of what changes in the starting material. So we need to break CC pi bond, and the product we need to form CH and CO. So we're breaking this bond, the pi bond, we're forming this bond and this bond. How do we go about doing that? We have an acid here. We know that's the acid. It's supplying a hydrogen. This has to be a base. The lone pair, or excuse me, the electron pair of the pi bond is what is acting as the base. And so if we consider this mechanism, we actually see that we have a bifurcation point if we call this the 1 position, the 2 position. Where is the hydrogen atom going to end up, at 1 or 2? And let's just evaluate both. We will draw both. That's important in the diagnosis of moving forward in this reaction. So if we're showing the top route protonating at position 2, the bottom route protonating at position 1. So this is supplying the electrons. Those 2 electrons are moving. That's what we mean by this double-headed arrow. 1, 2 electrons. These 2 electrons are moving. We are in the presence of acid. There's H+. Again, acidic medium, H+. That's provided by the sulfuric acid. We're going to go this route here. Carbon 1 is getting that hydrogen, meaning carbon 2 ends up as a carbocation. So now if we classify that, that is a secondary carbocation. But what if we were going the other route and we were giving carbon 2 the hydrogen? This is why you want to draw these things out so you can immediately compare them. Now that first position gets the carbocation. And this is where we have to decide. When the alkene is treated with the acid, it bifurcates. And so if we compare these in what we remember from Organic Chemistry 1, we see in our choice secondary versus primary. Secondary is more stable than primary. This route is going to be preferred. Now this is the electrophile. We're in the presence of water, which is a nucleophile. The nucleophile is supplying the electrons to the electrophile. We see that the oxygen's still protonated, so we have to do a proton transfer. I'm going to write PT for proton transfer, but simply it's just going to be another water molecule that is abstracting that hydrogen. And that's how we end up with our product 2-butanol. So as you can see in this first example of alcohol synthesis here, the alkene hydration, we've obeyed all of these rules in proposing this mechanism. In a second alcohol synthesis, using alkene hydroboration oxidation, we can see that if we start with the same starting material of 1-butene, and then in a two-step process, so one pot, two-step, in which the reagents are added at different times, if we have borane THF complex, and then sometime later we had hydrogen peroxide, sodium hydroxide, and water, we see that we're going to end up with a constitutional isomer of 2-butanol. In this case, we end up with 1-butanol, which has a melting point of -90 degrees C and a boiling point of 118 degrees C. So again, the relationship between 1-butanol and 2-butanol is that they're constitutional isomers. And so in this alcohol synthesis is a good example of what we're going to be doing in 256 this semester is taking a functional group and, depending on what the conditions are, transforming it into another functional group. So we're going to categorize this as we move through the semester according to oxidation states. So again, Module 1 is basically oxidation state 1 compounds, including alcohols, ethers, thiols, thioethers, and epoxides. So this is another example of, in terms of the arrow pushing formalism, you're encouraged to review prior screencasts on hydroboration oxidation. But the reason we get two different things from these different reagents is due to regioselectivity of the pi bond. So basically, in both cases, we're adding water across the pi bond, but the elements in which they add to each carbon atom are different. And so because we have different isomers here, constitutional isomers, they have different physical properties. And so it's important to understand the big picture of that. So in this last slide here for this screencast, we're going to talk about the reactivity profile of the hydroxyl group. And so what do we mean by that? We're going to look at how treating the hydroxyl group with different reagents basically is going to affect the inherent reactivity. So there's two modes of reactivity for our general hydroxyl group. So we see that the oxygen has two lone pairs and it has this acidic proton. Again, we have to keep in mind everything we learned from 255 is in play in 256. So the pKa of that OH has a pKa of 16. So again, as I mentioned prior, we have to diagnose the reaction conditions for a functional group and what the reagents are. So if we are in acidic medium, for example, and we have a general alcohol. I'm just going to use this as a substructure for a carbinol. We have these different substituents here. I'm not specifying them, just showing what the reactivity of the OH is under acidic conditions. And I want to represent the acid as HA, And I want to say that the H, we have delta plus and delta minus. That's the polarity of that bond. So under acidic medium, if this is an acid, this has to be a base. And so the action of a base is to abstract a proton. So we are forming an OH bond, and then we have to break that bond. So the arrows will flow as such. And again, the double-headed arrow indicates the movement of 1, 2 electrons. So this single bond has 2 electrons. The double-headed arrow is showing that both those electrons move and they end up on A. And so if we were to say this is happening under equilibrium conditions, the carbinol is now protonated. It's bearing now the positive charge, and we end up with the conjugate base of our starting acid, and that has a negative charge. So we've now balanced plus with minus. They balance their neutral. We're starting with neutral, so we have charge balance. So under acidic conditions, the alcohol will act as a base. But what about under basic conditions? So here's our general alcohol. Again, we're not specifying what those substituents are on the carbinol carbon. So now we're going to treat this with a base and say, let's say the base is sodium hydride. So sodium hydride is our base. We know that reactions take place with an acid-base pair or nucleophile-electrophile pair. So if that's the base, this is the acid. And we've diagnosed this is the most acidic proton that we're dealing with. So this base is going to abstract that acid. And following the logic from above, we would say this is delta plus, this is delta minus, and again we assign that based on Pauling electronegativities. So the negative is attracted to the partial positive. 2 electrons are moving. We're going to form H2. We're then going to cleave this bond. Notice the flow of arrows. They flow in one direction. The double-headed arrow is pointing to the partial negative. It's going to accept those 2 electrons. We move forward in the reaction. This oxygen now has formal negative charge, which is balanced by the metal cation sodium plus. We end up with H2. That's the conjugate acid of our starting base, sodium hydride. So that is actually a gas that escapes the flask. So that's why we're drawing this as a one-way arrow. The equilibrium is 100% this way. It can't go back that way because this has escaped the reaction medium. So this has been a review of how alcohol will react either under acidic and basic medium and how we account for charges in that medium. So again, to wrap up this screencast in Module 1, we're looking at the chemistry of alcohols, phenol and ethers, including epoxides, thiols, and thioethers. So these are all oxidation state 1. And so we'll get into what that means as well as more reactions of alcohols in the next screencast.